In this video, we will learn about how to derive the elasticity of substitution of a CES utility function. So by elasticity of substitution, what we mean, it measures the percentage change in the ratio of consumption of good Y to consumption of good X from a percentage change in the price ratio, that is price of good X to price of good Y. Okay, so our CES production, utility function will look like this. That is utility derived from the consumption of two goods X and Y is equal to, that is equal to A times X raised power beta plus 1 minus A raised Y raised power beta whole raised power 1 upon beta. Okay, this is our CES, that is constant elasticity substitution utility function. That is, utility is a function of the consumption of two goods X and Y. Here this A denotes, or it is actually share factor, or we can also say it is the distribution factor. Okay, it simply shows us the share of utility derived from the consumption of good X, and this 1 minus A denotes the share of utility derived from the consumption of good Y. This beta is our substitution parameter. Okay, now how do we find the elasticity of substitution? Let us first write the formula for elasticity here. Okay, and let me write it here. Let's denote elasticity by this rho. So elasticity is simply equal to change in Y upon change in X here, or rather change in what we have here, P. Let me write it here, P times P upon Y. Okay, so this is the elasticity formula, where this Y represents, and let me write it here, this capital Y is simply the output ratio, the goods ratio, that is Y upon X. Since Y and X are the two goods, this capital Y denotes the ratio of these two goods, and this P shows the price ratio, that is Px upon Py. Okay, I hope I am making myself clear. Now we know that first order condition for utility maximization requires, and let me write it here. So first order condition for utility maximization requires, as we know, it is that our marginal rate of substitution between goods X and Y should be equal to the price of X upon price of Y. Okay, and we know that this very thing, MRS is simply the marginal utility of good X upon marginal utility of good Y, and it should be equal to price of X upon price of good Y. Now what is marginal utility of good X? That means we need to partially differentiate this utility function with respect to X. Okay, so let's write it here. Our MUX will be equal to the partial derivative of utility function with respect to X. Okay, so if we take the partial derivative of this utility function with respect to X, so we will be using here chain rule. Okay, first this 1 upon beta will become the coefficient by power function rule, so we have 1 upon beta. Then we have this whole term, that is a x to the power beta plus 1 minus a y to the power beta, okay, raised power 1 upon beta minus 1 by power function rule, and using chain rule, that is d upon dx of this a x raised power beta. Okay, I hope I am making myself clear here. So first we use the power function rule, and then we multiply and internally differentiate this, because x is involved in the first term only here. So solving this, it will give us and let me write it here. Okay, so let's solve it here. So we have 1 upon beta uh, a x raised power beta plus 1 minus a y raised power beta. So this is 1 minus b, 1 minus beta, 1 minus beta divided by beta. Okay, then the derivative of x will be here. It will become, so this beta will become a coefficient, so we will have beta times a x raised power beta minus 1. So this is our marginal utility of x. Symmetrically, we can calculate the marginal utility of y, and let me write it here. Marginal utility of good y will be equal to the partial derivative of utility function with respect to y this time, again using chain rule here. So 1 upon beta will become coefficient. Then we have this utility function a x to the power beta plus 1 minus a y raised power beta whole raised power 1 upon beta minus 1, and then we use the chain rule, that is d upon dy this time, and take the derivative of this 1 upon a y raised power beta. Okay, so we have 1 upon a, okay, y raised power beta. Bracket the okay. So doing the calculation here again, so we have here 1 upon beta a x raised power beta plus 1 minus a y raised power beta. So again it will become 1 minus beta divided by beta. So here again by power function rule beta will become coefficient, so we will have here beta, then 1 minus a y raised power beta minus 1. Okay, this is our marginal utility of good y. As we have told you that the first order condition for utility maximization requires that marginal rate of substitution between x and y should be equal to the ratio of prices. So this is marginal utility of good x, and this is marginal utility of good y, and we equate it with the ratio of the prices. So let's write it here, which implies, so we have this function first, that is 1 upon beta, then we have a x to the power beta plus 1 minus a y raised power beta whole raised power 1 minus beta upon beta times beta times a x raised power beta minus 1. To this we divide the marginal utility of good y, which is this 1 upon beta. We have a x raised power beta plus 1 minus a y raised power beta whole raised power 1 minus beta divided by beta. Okay, this is here in exponent times beta times a, no, we have beta only, then we have 1 minus a. Okay, let me write 1 minus a raised power beta minus 1. So here you can see we can cancel like terms, beta and beta get cancelled, these whole terms get cancelled, this term gets cancelled with this 1 upon beta with this. So it should be equal to price of good x upon price of good y. So let us see what we are being left out here. So what will we get here? We got here a upon 1 minus a raised power beta minus 1. Okay, beta minus 1. Sorry, it is not raised to power anything. Kuch khabar kabir. we have then x and 1 upon a. Sorry, let me see if I am doing any, you know. So here we have actually y raised power beta minus 1. Sorry for this mistake. So we have here x raised power beta minus 1, y raised power beta minus 1. So I can write it in this fashion. X upon y raised power beta minus 1 should be equal to price of x upon price of y. Okay, I hope I am making myself clear here. Okay, so we need to solve this function. First we need to find out x upon y only. So we can do, actually we need to find out the y upon x. Sorry. So can I do one thing here? So we have here x to the power beta minus 1, y raised power beta minus 1, a upon 1 minus a is equal to price of x upon price of y. Let us reciprocate this. I can do it. If I transpose numerator to denominator here, okay, if x is in numerator, let's transpose it to the denominator. So in denominator it will become x raised power minus beta plus 1. So exponent sign gets changed. And symmetrically, if I transpose this y here, it will become y raised power minus beta plus 1. Okay, so this can be written as y raised power 1 minus beta. Here we have x raised power 1 minus beta, and I can write it in this fashion y upon x raised power 1 minus beta, isn't it? I have done nothing unusual here. Okay, simple transposition here. So in place of this I can write y upon x. So we have y upon x raised power 1 minus beta times a upon 1 minus a should be equal to price of x upon price of y. So let me rub this out. Mission zurtiya. We need to solve this for y upon x. So we have y upon x raised power 1 minus beta will be equal to price of x upon price of y. If I transpose this, it will become 1 minus a upon a. Okay, now transpose this exponent, it will get, it will become exponent but in reciprocal order. So we will get, and let me write it here. So we will get y upon x will be equal to, if I reciprocate it, so it will become price of x upon price of y. Let us give this exponent to each of these terms. So it will become 1 upon 1 minus b. Simple thing, it is exponent here. When I transpose it, it will become exponent, but it will get reciprocated. If it is 1 minus beta, it will become 1 divided by 1 minus beta. And it will be also for this 1 minus a upon a raised power 1 upon 1 minus beta. So we got this ratio here. Now what we need to do here, as we have told, elasticity of substitution is simply change in y upon change in p into p upon y. So we know that our y is equal to this thing. So let's transpose this here. So we know that our elasticity is equal to change in y upon change in p times p upon y. Okay, now this change in, okay, let's write it here, which is so change in y upon change in p will mean change in, so y is equal to y upon x. So we have y upon x. Change in p means p is equal to px upon py, px upon py. Okay, times p is again px upon py, ratio of the prices, divided by our y is equal to y upon x. Okay, y upon x. So what we need to find out, we first need to find out this very derivative. Okay, since y upon x is a function of price ratio. So we take the derivative of y upon x with respect to px upon py here. Okay, so let's take the derivative now. Considering this, its derivative, that means del y upon x with respect to price ratio, that is del px upon py, it will be equal to, let's take the derivative here. So what will it come out to be? So we need to find out the derivative of this px upon py here. Again, by power function rule, 1 upon beta will become coefficient, so we have 1 upon 1 minus beta. Okay, then we have px upon py. Okay, then we have 1 upon 1 minus beta minus 1. Okay, I have simply taken the derivative of this y upon x with respect to px upon py. Okay, nothing unusual here again. So using this formula here, so elasticity of substitution will be equal to, so this we got equal to 1 upon 1 minus beta upon px upon py raised power 1 upon 1 minus beta minus 1. Okay, dx upon dy times px upon py, let us write it px upon py divided by y upon x, and let us divide it by 1 upon y upon x. So y upon x is this whole term. Okay, let us write it here, dividing it by this whole, because y upon x is this. So we have px upon py raised power 1 divided by 1 minus beta times 1 minus a divided by a raised power 1 divided by 1 minus beta. Don't get confused. I am just using this whole term. Okay, is this. Okay, px upon py as it is divided by y upon x. Okay, don't get confused that this is in numerator or denominator. It is one term, that is the derivative. So let us see if anything gets cancelled here. Okay, so let us see it perfectly. Uh, uh, and let's write it here is equal to this. Okay, so we have here 1 upon beta. Let me write it here, 1 upon 1 minus beta px upon py. Let's expand this, px upon py raised power 1 upon 1 minus beta. Okay, so times, I can write again px upon py. Okay, raised power minus 1, raised power minus 1. Then I have px upon py. Okay, this is our numerator, and in denominator what we have, px upon py raised power 1 upon 1 minus beta. Then we have 1 minus a upon a. Okay, 1 upon 1 minus beta. Let us see if anything gets cancelled here. So first thing is this will get cancelled with this. Okay, and let me see if I have missed any term here. Yes, I have missed here the term, that's why. So here we will have, when I take the derivative of this function, then I have this term also here. Okay, that's why I was getting confused where actually it got. So here we have this term again, 1 minus a upon a. I forgot to write it, my mistake. Raised power 1 upon 1 minus beta. Okay, so this term will be here also. Okay, here let me write it here, we have 1 minus a divided by a raised power 1 upon 1 minus beta. Okay, so here we have again this term. Okay, you can see 1 minus a upon a raised power 1 upon 1 minus beta. I forgot to write it, my mistake. So this term will get cancelled with this term. So if I transpose it here, so I will get 1 upon 1 minus beta. Then we have price of x upon price of y. If I transpose it, it will get here px upon py. Okay, and its exponent sign will change. It is -1, it will become +1. This gets cancelled. So our elasticity of substitution came out to be 1 upon 1 minus beta. This is the elasticity of substitution of this constant elasticity substitution utility function. By definition, that means the elasticity of substitution of this CES utility function is constant. Okay, and there are some things. If this beta, and let me write it here, if I have, if this beta tends to 1, that means if it approaches to 1 by limit, so we will get linear utility function. Okay, let me write it in this fashion. If this beta in elasticity of substitution approaches to 0, we will get Cobb-Douglas utility function. Okay, and if this beta approaches to, if b approaches to negative infinity, we will get Leontief utility function, that is perfect complement utility function. Okay, this is how do we find out the elasticity of substitution of CES utility function. I hope I make myself clear in this video. Thank you.